Hello, everyone. This is the last stuff of the semester, fluids and pressure. So, what we're doing here is extending stuff that we've already known about the motion of objects, and we're going to extend it to stuff that's a fluid, stuff that we can't treat as distinct objects like, this ink pen. Instead, we have to treat it more like a flowing substance like water. And so we don't have a distinct object. We have a continuum, a bunch of stuff, and we can only look at the properties of the environment in a sense. So we're going to define pressure here. And the idea is it's a very simple thing. If we apply a force, it's going to be applied over some area. Pressure is force over area. And I'm going to, in a second, tell you why we care about that. So what I have here, push pin, right? You've seen these in the classroom. And if I squeeze it like that between thumb and finger, and if you did this gently, not too hard, you know which one would be uncomfortable first. The idea is that the thumb and finger are basically putting the same force on this push pin. They have to be, otherwise it would be moving, and it's stationary right now. So the thumb and the finger are doing the same force, but one of them causes more discomfort because the force is being localized on the tip there. It's a tiny area for this force, so it's a high pressure, whereas on the head end, it's a wide area, so it's a lower pressure. So we're going to look at the pressure of things. So this has some reasonable units. The units here are 1 Newton per meter squared as 1 Pascal. It's reasonable enough. And so we can talk about the pressure that various things feel. So one obvious thing that comes up is the atmosphere. We don't usually think of it as having pressure because we don't feel it in a sense, unless we feel a change in it. Sometimes your sinuses get blocked up and that hurts because the air pressure changes. But on something the size of this sheet of paper, right, this is roughly a square foot. There's about 15 pounds of air pressing down on it, roughly, right? And so the air has weight. And what we're talking about is a column of air, the shape of this area, and it goes up to the top of the atmosphere. And so we can talk about the pressure that the atmosphere puts on. So the pressure of the atmosphere we state as a standard number because we know it varies, but we just need some number that's standard, and it's 1.013 times 10 to the 5 Pascal, which is about 100,000. And this is going to be the thing that we call 1 bar. If you ever see that unit in other places, 1 bar is 100,000 Pascal. Now, there are other versions of this. Right, is other units. I kind of talked about it when I talked about the square foot of paper and the 15 pounds. Right, there's pounds per square inch, and then there is inches of mercury, or right. And so there's different forms of these units, and they have different conversions, but um, the gist of what we're going to work with is basically pressures on the order of a few Pascal to a few 100,000 Pascal. Right? And we're going to use the standard units. We're not going to go into these, but you may see them other places, and I'll tell you where some of these come from. It's obvious pounds per square inch coming from the definition, but inches of mercury kind of seems weird. And it comes from a column of mercury of some size has some weight. And so you take the weight divided by the area it sits on, and what you're left with is the height. And so this is a pressure equivalent to a certain amount of mercury. And you can also have a pressure equivalent to a certain amount of water. So let's go into what we can do with pressure here for a bit. So I want you to imagine here is our water, a big thing of water. And water has fish in it. And we put waves, and then there's going to be some air up here. Now, by definition, we know right there the pressure at the surface is 100,000 Pascal. It's the pressure of the atmosphere. But what about somewhere lower down in here? Well, what we can do is draw in two places here. And this is, we're taking a chunk of water. It's liquid, but it's a chunk of water. And so there's some forces acting on this. All right, is this chunk of water is not moving up or down or left or right, so the forces are balanced on it. And there's some force from the side, and there's some force from the other side, and there's force going into the page and out of the page. These are balanced, and the forces in and out of the page are balanced. But on top, this force happens to be the weight of everything above it, and this force happens to be everything below it being pushed in, right? And so we can label it. This is going to be pressure 1 times area, and this is going to be pressure 2 times area. So the difference in these has to be based on the weight of this block of water. And the weight of the block of water is rho GH times the volume, right? No, it's rho G times V. Yeah, that's what it's. Density times volume times G. So the weight is mass times G, but we know mass can be written in terms of density. So density times volume times G. And I should be clear about this is when we write density is mass over volume, our symbols here are going to be rho is M divided by V. Okay. So here, what we have here is if we add up the net force on all of these things, so right here we're going to look at the net force, and so we'll have upwards, and this should be 0. We're going to have upwards, we're going to have pressure 2 times the area, and then we're going to have pressure 1 times the area, and it's in the opposite direction, and we're going to have the weight of the water. So we can also note that this rho GV, volume is really the area times the height. So we have a common area in all of these, and so if we rearrange this, what we'll get is that the pressure at this lower point is the pressure at the higher point plus rho GH. So this tells you the pressure in any fluid at some point given a known pressure. So one of these pressures is known, you can figure out the other one based on the weight of the fluid. Now in this diagram, we know the weight of the atmosphere above, so we know the pressure on the surface. We can figure out what the pressure is down here. So let's pick a point, and let's say that is 30 meters deep. What is the pressure there? Well, we can do this. We can say that the pressure at H is 30 meters is, well, we're going to have the pressure at the surface, that is 10 to the 5 Pascal, or in your problems it should be 1.013 times 10 to the 5 Pascal. Plus, now it's going to be the weight of the water above that point divided by the area that we're looking at. All right. So it's going to be this rho GH. So density of water is 1,000 kilograms per meter cubed. The density of air is about 1.3 kilograms per meter cubed. About. It varies a good deal. So the weight of the water, or the density of the water, the weight density of the water is going to be 1,000 kilograms per meter cubed times 9.8 meters per second squared times 30 meters. I'm running out of space here, and the computer just fell asleep. There we go. So we have some calculation there, and the gist of this, it comes into a nice sort of rule of thumb that we have basically for every 10 meters that we go down, we're adding an atmosphere of weight. Because what this is 1,000 times 9.8 is 10,000 times 10 is 100,000. So this is about 300,000 Pascal. And you can check your units. You'll have kilogram per meter squared. Newtons. So you'll have newtons out of kilograms and meters per second squared, and then you'll have meters divided by meters cubed. That is a pressure, so you'll have Pascal. And so out of this is the pressure at 30 meters is about 4 times 10 to the 5 Pascal. Of course, in your WebAssign, you'd use more precise numbers. This would be like 296,000, something like that. And this would be 1.013, and you'd add them. So this is the ballpark. The idea is that you set up problems like this, and this is just essentially one equation, plug and chug. So there's some other questions going on here. Right? Is that what if we want to do problems like you're in the air and you want to know the air pressure above you? So you're climbing a mountain and you're up, say, 3,000 meters. So the pressure here, I'd like to know how much that is. So we'll take that our density of air is 1.3 kilograms per meter squared, and we'll do the same sort of math. Now here, the known point is the lower point. You order these by height. So P2 is the lower point. So P2 is P1 plus rho GH. So P2 is 1.013 times 10 to the 5 Pascal. And that equals P1 plus 1.3 kilograms per meter cubed times 9.8 meters per second squared times 3,000 meters. Let me rewrite that. All right, and so we're solving for P1, and this is where we pull out a calculator to check that things make sense. 1.3 times 9.8 times 3,000 is not that much, about 38,000, and we're going to subtract it from 1.013 times 10 to the 5, and we get our pressure, P1, is about 63,000 Pascal, which is 0.63 times 10 to the 5 Pascal. So comparing, if you climb up 3,000 meters, so this is about 10,000 feet, so think Rocky Mountains. mountains. Think above Denver, but not quite at the top of the mountains. There's only about 2/3 of the atmosphere above you. Sorry, there's only about 2/3. You've covered 1/3 of the atmosphere in 3,000 meters. And so what happens is in the atmosphere, it tends to go like that. It's not exactly the detail, but it's an exponential decay for pressure. And then in fluids, it works the other way. Is the deeper you go, the more, the lower you get, the more negative your height, the deeper the pressure goes. All right. So let's stop that video and we'll do another one here.